Hi there, my name is Harold Schuch. I'm a lecturer for the Department of Civil Engineering at the University of Colorado, Denver. I'm here to present you a module that deals with total stations, that principal survey instruments for surveyors and engineers. What you see here is a picture of a total station courtesy of Trimble. We have an instrument that consists of a telescope. This telescope can be rotated around a horizontal axis. This instrument can be secured to a tripod, for instance, with the help of a screw. This instrument can be leveled with the help of 3 leveling screws. In other words, this instrument has a vertical instrument axis, and this vertical axis should coincide with the local plumb line. With a little more detail, we have here the telescope with its focusing ring. This is to focus the image. The telescope also has an eyepiece that contains crosshairs that are used for measurement. The focusing of these crosshairs is done with this focusing ring here. For the purpose of leveling this instrument, which is not self-leveling, there is a bubble on this surface, and we'll see more of that later on in this presentation. Then we have an instrument display that displays horizontal angles, vertical angles, and distances. Did I say vertical angles? Yes, because here we have a circle, what is called a vertical circle, that is used to measure the inclination of this telescope. So if the telescope is inclined 45 degrees up, then this would show plus 45 degrees. This is captured electronically and displayed on the display. Then we have the horizontal circle, which provides us with the ability to rotate this instrument either left or right and obtain directions of angles in the form of angles. Now, if we want to rotate this instrument left and right very carefully and very finely, we can use this screw to do this. We can also adjust the vertical angle of the instrument very carefully by using this vertical adjustment screw. These 2 screws are used for very fine aiming adjustments, which allows us to be very precise with this instrument. Last but not least, we have a laser beam that is installed in the base of the instrument. This base is called the tribrach, and it has a laser plummet installed. This laser plummet creates a laser beam that shines downwards towards the ground, and this beam coincides with the vertical axis of this instrument. So in other words, if the instrument is level, then this beam coincides with the local plumb line. Now, if we want to measure a distant point using such an instrument, then we would have to set this instrument up on a known point, let's say a point for which we know the 3 coordinates, x, y, and elevation. And to set the instrument up on this point, we use a tripod. And the laser beam, the optical plummet, should shine right on top of this point of interest. Now, we place a reflector on the point of interest that we want to measure. And what we do is we measure the slope distance towards that point. And there are 2 things that we should never forget, and that is that here the instrument is a certain distance from the ground. It is not right on the ground. As a matter of fact, it would be impossible to put this point right there. Then the instrument would be half buried in the ground. So we have an operating height here. Let's say the operator leaves this at 5.5 feet height, thereabouts. Then we have an instrument height, or the height of instrument. This has to be measured with a tape and recorded. And the prism also is standing above the ground on a staff. The length of the staff from the ground all the way to the center of the reflector has to be measured and recorded as the height of reflector. So this is a simple view of a measurement and the intent to measure something if we look at it in such a view that is a vertical plane that contains both the instrument and the reflector. And this measured slope distance is also within the same vertical plane. Let's take this into a little more detail. So again, staying within this profile view, we have the instrument measuring a slope distance. And not only does it measure the slope distance, it also measures a vertical angle. From the slope distance and the vertical angle, and the cosine of this vertical angle, we can calculate the horizontal distance between the instrument and the reflector. And taking the sine of this angle and multiplying that by the measured slope distance gives us the vertical distance. So if I then want to calculate the elevation of point B, that is simply an exercise of taking the elevation of point A plus the height of instrument, plus the vertical distance, minus the height of reflector. And that's the equation for it. So that's why the height of the instrument and the height of reflector are as important as the instrument measurements, such as angle and slope distance. Now, the problem is that nothing is perfect in the sense that we wish that all the measurements were done perfectly. It is not so the case. But also the instrument has internal error. The reflector has internal error in the sense that this reflector does not return the signal from its center. In fact, this laser beam actually bounces around in the reflector before it is thrown back. So there's a path within the reflector that has to be taken into account. And there's also the laser gun is not exactly at the center of the instrument. There's some error there. So there is a fixed part of an error of every measurement. That is the internal error of the instrument and the internal error of the reflector. And that is called the error constant. This does not change from one measurement to another. Now, there are calculation errors in the instrument that take the distance as determined and reports it back. But this error is not constant. It changes by the length of the distance. So here you have the total distance error then is a constant value plus or minus the instrument error in part per million. And this is what vendors give you for the purpose of being able to correct, if necessary, measurements that you take with this device. So every instrument is calibrated every time it is either manufactured or serviced for the purpose of determining these error levels. Now, in terms of operating the instrument, the working principles thereof, let's imagine that we are looking at the instrument in perspective. Here you have a horizontal circle. This is the circle along which horizontal angle readings or directions are measured. Then we have a telescope, and the tilt of the telescope is measured along this vertical circle. These are shown as ellipses because we're looking at it in perspective. This red arrow here is the vertical axis of the instrument, and this is supposed to be the location of the point we are positioned on. Now there's a significant difference between the horizontal directions and the vertical angles. And I will talk more about the difference between angles and directions. But let's start with this. The telescope would be leveled with the instrument. And when the telescope is directed towards its zero vertical angle, then this telescope would be in the horizontal plane, or the optical axis of the instrument would be in the horizontal plane. If the telescope is tilted up towards a point, let's say, then it will be able to measure a vertical angle that is from the horizontal plane up to this line of sight. So the instrument will in fact display vertical angles, either positive or negative, for every distance measured. And that is the advantage of having a vertical axis and an instrument that is leveled. The situation is different when it comes to horizontal direction reading. The instrument will have its zero horizontal direction. So right around here, the reading will be 0 degrees. And let's say over here, the direction would be 90 degrees. The instrument does not know where north is. It does not know that. So there's a big difference between the horizontal readings and the vertical angles. The instrument does not give you horizontal angles. We have to calculate them from the difference of two directions. Now, in relation to distances, we have a slope distance reading to the prism, which gives us a horizontal distance and a vertical distance on the basis of this vertical angle. This distance comes from the electronic distance measuring device, the EDM device. Some instruments calculate the horizontal distance for you, and so it does for the vertical distance, which is very convenient. You can record those instead of just the slope distance. Now again, let's come back to the idea of directions versus angles. When the instrument is leveled, then its vertical axis is parallel to the plumb line, or it coincides with the plumb line. This allows real vertical angles to be measured with the instrument. You can write them down directly as vertical angles. However, the instrument does not know where north is. Therefore, if we want to measure horizontal angles, then we have to measure, for instance, for each angle we have to measure 2 directions, and from those directions calculate angles. And this calculation would be basically one direction minus another direction. Drawing this, it would like this if the instrument is looked at from the top. Here we would have direction 1, and here we would have direction 2. Each one of those directions would give you a specific horizontal circle reading, and you take this reading minus that reading to calculate the angle. This is something you have to do. There is a possibility in some instruments to set this direction to a reading of 0 degrees, but it is normally considered too wrought with error to perform that on a consistent basis. It is much better to take 2 directions, whatever the instrument shows you, and then calculate the difference. So this is the view of the instrument from the top. Let's look at the instrument from the side. In this case, we look along the horizontal axis of the telescope. This is the axis along which the telescope rotates. This would be the top of the instrument, and this would be the horizontal plane if the instrument is leveled. Then the instrument is able to give you, let's say, a vertical angle from this horizontal plane to the prism. Let's say that this is 50 degrees, this vertical angle. So many instruments will give you this vertical angle. However, some instruments don't give you that. Some instruments give you the zenith angle. The zenith angle is measured from vertical downward. So this angle would be 90 minus 50 or 40. So 40 degrees measured this way. So vertical angles are measured either positive, up from the horizontal plane, or negative. So vertical angles are valued from 0 to 90 and from 0 to minus 90. In contrast, zenith angles are only positive, and they're measured only from the top, from zenith, and they can vary from 0 to 180 degrees. So this is the story about the zenith angle. Be careful what the instrument displays, and when you record measurements, make sure you record also what kind of vertical angle the instrument is giving you. You can incur major errors if you don't do that. Now, let's look at the way in which instruments are set up. What does that mean? This is the method to place an instrument on a point for the purpose of making a measurement. And there are certain things that have to be satisfied. For instance, the instrument has to be exactly above the point along a vertical line, along a plumb line. And to achieve that, we will follow this stepwise process. Each one of these steps is further explained in a separate slide. So essentially what we will do is we'll set up the tripod over a point. We'll place it closely over the point, roughly level. We will see what that means. Then, so this is the first step. This is actually just taking the tripod and place it over the point. Then the instrument is placed on the tripod and turned on. Then the laser plummet dot is moved onto the point by rearranging leg positions. That's right, this sounds strange, but you are lifting one leg at a time to adjust the position of the dot on the ground. Then the tripod is leveled by adjusting the leg lengths in the instrument bubble. Then the instrument is leveled with the internal electronics on the display. And finally, the instrument is shifted on the tripod so that the laser plummeted dot is located exactly on the point. Step 1 then, in a little more detail, is this one. You take the tripod, you open it up as shown, and you loosen loosen the clamps and you extend the legs to your preferred height. Then you secure the clamps and place this tripod so that this top plate of the tripod is close to the position of this point of interest. This is where you want to set up the instrument. So make sure that the clamps, after this operation is completed, are tight and secure, and that the feet don't slide on the ground. If you are set up on soft soil, you may want to step on this little ledge and push the tip into the ground for greater security. As step 2, you're using 2 hands to position the instrument at the center of the top of the tripod. Then you use the screw that is at the bottom of the tripod. You take it through the hole and screw it into the base, into the tribrac of the instrument, and secure the instrument on that surface onto the tripod. Now just tighten lightly, just hand tighten, don't tighten too hard. At this point, you turn on the instrument. And here you see a fat red arrow. This is supposed to depict the laser plummet. At this point, it will shine to the side of this point. It will paint a small red dot on the ground. Now, you hold one leg with one hand and you grab another leg and you gently lift it and you move the tip, the foot of that leg a certain distance, and you will notice that the little red dot will also move, and you move this leg so that this dot moves closer to the intended point. And you repeat this process with the other legs until this dot is close onto this point. It doesn't have to be right on, but it should be within half an inch or so. Then make sure again that the legs are secure in the ground. In the next step, you will level the tripod. And you level the tripod by looking at this bubble at the top of the instrument. You loosen one clamp at a time and lengthen or shorten each leg until the bubble on this instrument is close to the center. When I say close to the center, the bubble should be at least split in half by the circle that is etched onto the glass surface. Now, every time you move one leg, make sure you tighten the clamp again. So you repeat that with the 3 legs until you reach this condition or better. Now you level the instrument, and you do that with the help of the display that shows a diagram such as this. What you want to do is you want these black dots to be at the center of their range of movement. And you do this adjustment only with these 3 adjustment screws on the instrument. Once you reach this level point, then the instrument is level in general, but the dot is still not on the point. It will be off by a small amount. So what you do, you loosen the clamp a little bit so that this instrument slides on this tripod surface. You make sure you don't rotate the instrument in any way, left or right. You just shift it in a parallel fashion, left or right or up and down, so that this dot ends up on the point of interest. It's also important at this point to make sure to record the height of instrument. So you want to make sure that before you go to the next step, you tighten the clamp again that holds the instrument, and you have set up the instrument ready for measurement. Now, when it comes to focusing the instrument, you have the focusing ring of the telescope and the focusing ring for the crosshairs. You always focus the crosshairs first because this is something that adjusts the eyepiece to your eyes. Once that is done, you want to focus the image through the telescope. So always focus the crosshairs first. Why is that important? Because each part of the telescope has its own image plane. If the image plane of the crosshairs after focusing is different from the image plane of the telescope, then the possibility exists that the crosshairs will move with respect to the image. You don't want that. So make sure your crosshairs are fully focused before you do any telescope focusing. Now, I mentioned the measurement of the height of instrument, and I mentioned that this telescope has a horizontal axis along which it turns vertically. This axis is actually the center of that axis is marked with a dot on the side of the box that holds the instrument. This has a dot, and that dot is the one to be used for the measurement of the height of instrument. So the instrument is ready for use. For that, Please check out the module on three-dimensional traversing, which will explain how to measure a complete traverse or a loop of measurements. I hope you'll enjoy that too. Bye-bye.